Hi guys, welcome to Embedded DSP Design on FPGA. Today's video is a continuation of part 1 of FIR dual channel design. In the first part we designed a dual channel FIR filter, and today I would like to do a live demo that validates the performance of this filter. You guys can see on my scope here what you guys see on my scope right now is a frequency sweep. So I have a DDS on my FPGA that does a frequency sweep from 100 Hertz all the way to 500 kilohertz, and we have an increment of 100 Hertz, and each frequency stays persistent for 10 milliseconds. So you can see that at some point in time the frequencies start to attenuate, and the expected value at which these frequencies are supposed to start attenuating, or the 3 dB point, is 100 kilohertz. So we will try to roughly validate that on the oscilloscope. The DAC I'm using here, if you would like to know, it is AD5445. You can read about it, and the output of the DAC is 12 bits, and it swings between 0 and -10, as you can see on my scope. So we have a division of 5 volt per division. So I will stop it shortly to just kind of look at where exactly the attenuation starts. So the attenuation is supposed to start after 10 seconds, because 10 seconds corresponds to about 100 kilohertz. I mean, roughly you can see like the amplitude of the output frequency starts to attenuate roughly after 10 seconds, and the frequencies totally get attenuated roughly around here, pretty much 228 seconds. That corresponds about 280 kilohertz. So, or more specific, more to be precise, they are supposed to be totally attenuated at 300 kilohertz. So there is a spur here. You can see this is not a spur, actually, it's just a glitch on my DAC, so don't have to worry about it too much. So that's pretty much it in terms of what's happening about the frequency response in time domain. So yeah, so the DDS, like technically here again, I'm supposed to be looking at two outputs, the I and Q, but because I have only one DAC, so I'm looking only at the I component of my FIR filter. So shortly we will move to Vivado. I will walk you through the code, and at the same time we run a live demo on the ILA or chip scope, and we'll look at both the I and Q waveforms and see how the performance is. So stick around, I will move to the Vivado right now. So this is the code I have for this live demo that I just shared with you. So basically what I have a DDS within the FPGA, and this DDS, it does a frequency sweep from 100 Hertz all the way to 500 kilohertz, and there's an increment of 100 Hertz. So basically it goes 100 Hertz to 100 Hertz and all the way to 500 kilohertz, as I said, and each frequency persists for 10 milliseconds. That's why I put this counter here based on the clock frequency that I'm using. The clock frequency I'm using is 200 megahertz, and also the FIR clock is also 200 kilohertz. So briefly here on the top level I can show you this is the DDS instantiation. So I have an index that I use this frequency index to tell me at what frequency we are at, and that will show at the ILA, because there is a correlation between the frequency index and the value of the frequency we are looking at. So I will explain that later once we get to it. We have an output for the DDS, which outputs the frequencies of interest, and the input, of course, is the phase increment. And I explained that in my previous tutorials about how the DDS works. So if you guys are interested, you can look at the DDS video and you will understand how this configuration was done. So the DDS module is here. I will leave this a copy of this code on my GitHub and you can go through it, and if you have any questions you can ask me about that. So we have a clock and the input is 32-bit. 32-bit, that's the phase increment, and the output. So the output here is 16 bits, and why it's 16 bits? It's just actually because we have two channels. Each channel is only 8 bits. So for the I component we have 8 bits, and for the Q component we have 8 bits. And then we are doing our sweep based on as I mentioned before, like the start and the end of our sweep. So we are starting from 100 Hertz all the way to 500 kilohertz, and then the persistence, for how long we want each frequency to persist. So that's pretty much it. So this code, I went through it last time in my previous video. Please go back and take a look again if you have more questions. So it just basically, it's a counter basically that keeps track of our frequency sweep. So in total I have about 5001 points, and each increment is, as I said again before, 100 Hertz. So that's pretty much it. I don't see much here to discuss about this because I discussed that in the past. And the output of the DDS goes to the filter, to the FIR filter. This is it. So the input is supposed to be 16 bits, like each channel is 8 bits, and the output is supposed to be here 48 bits, so each channel is 24 bits. And the output of the filter goes to my DAC. So DAC is over here. So as you can see here, the first channel is assigned to channel 1, channel 2, and then the data that I sent to the DAC is like in this case I selected channel 1, like I just showed you on the scope. But for the Vivado here I'm doing an ILA live demo, so you're gonna look at the ILA. I'm sending this channel to the ILA, and this is how I assigned them. So I took bit 15 to bit 5, and I took also bit 39 to bit 29, and bit 23 and bit 47 are sign extensions. So you can quickly look at the ILA here, what we have at the ILA. Just a second. So this is the ILA. We have channel 1 and we have channel 2, and we have the frequency index. As I mentioned to you guys, the frequency index has a correlation with the frequency of interest. So if you have, for example, an index of 10, that means we are at 1000 Hertz, 1 kilohertz. So we always multiply by 100 because each index corresponds to an increment of 100. So I think time now to go to the ILA and look what's going on. So we come here. I already connected everything, so it's already connected. I'm going to run it just now, and we can look at the performance of the filter. So it's running now, capturing data. So right now you see basically there's nothing coming out. Let's make this bigger. And why nothing is coming out? Look at the index here. The index here is 4359, and this corresponds to 435.9 kilohertz. So definitely no signals are going to be coming out from the filter at this point here. So we repeat again. Same thing, nothing coming out, and this is because the frequency we are looking at right now is 283 kilohertz, so it's not coming out. So another one. So our passband is supposed to be between 0 and 100 kilohertz. Seems like we are not lucky yet with capturing low frequencies. One more. We have to be fast. Okay, here you go, we got something here. So this corresponds 872, it corresponds to 87 kilohertz. So great, let's focus more on this 87 kilohertz. Zoom in more. So I just want to here show you something about the phase difference. So these are supposed to be quadrature components. The top one is the I and the bottom one is the Q. So let's confirm that. So exactly, so difference is 90 degrees between the 2 pi over 2. So this is the I, this is the Q, and the value of this component, as I mentioned, is 87K. So we'll run another one. So this is 90 kilohertz. Quickly run another one. This is 247 kilohertz, 0.4 kilohertz. So as you can see, it's totally attenuated. So we can do another one again, see how much luck we have with this again. So nothing here. This corresponds to 402.9 kilohertz. Let's see if we can get another low frequencies better, just for the sake of demo here. So far we have luck only with high frequencies. There you go, we got low frequency here. So this one corresponds to 48 kilohertz, 48.9 kilohertz, and as you can see, it passed through nice and clean with the right attenuation. So the attenuation expected here is around 2000. That's exactly what it is. Same thing here, 2000 I and Q. So I guess this is it for my demo. So I was planning to show you a frequency response on the spectrum analyzer, but due to some technicalities, I don't have the tools ready, so I just did, as I showed you, the frequency response in time domain and this ILA chip scope capture, live capture. I hope you guys enjoyed this video, and please stay tuned for the next video sometime next week. And I'm planning to talk about down conversion, mixing down conversion, and again, all this stuff is related to the final project I intend to implement, which is the design of an FM radio receiver. Thank you and good luck to you, and talk to you next time. Bye.